My name is Kailas Jawadekar, and I'm a developer advocate for the Oracle MySQL community team. And welcome to the presentation on managing MySQL InnoDB cluster with the MySQL operator on Kubernetes. Let's get started. So we know that the hard part is not starting MySQL. The hard part is the day-to operations, operating MySQL consistently. In this presentation, we'll demo a MySQL operational loop. We'll show deployment, routing, recovery, configuration, backup, and restore. If we only show the first pod coming up, we have not really demonstrated the database operation. The center of this slide is the MySQL runtime. In this demo, that runtime is stateful, replicated, and backed up. It's not just one container. It's an InnoDB cluster with multiple MySQL instances, as well as router, persistent volumes, Kubernetes services, secrets, etc. We start with deploy. The declared cluster creates three MySQL instances plus the router. That gives us a runtime with replication and routing layer. Route. The application does not connect to a specific pod name like demo MySQL 0. That would basically bake topology into the app. It connects through stable services and the router. So topology changes are handled below the application layer. Recover. In the live demo, we identify the current writable primary and delete that pod. Then Kubernetes replaces that pod. InnoDB cluster elects a writable primary, and the operator and sidecars converge the database topology back to a healthy state. Configure means we patch the declared MySQL configuration. The configuration change is expressed in the InnoDB cluster spec, and the operator handles how that flows into the generated configuration. Protect or backup. The backup is a MySQL backup resource that writes a MySQL shell dump into a backup PVC. The restore then creates a separate cluster initialized from that particular backup. So the key takeaway is manual operations drift, but declared resource definition gives the platform something specific to watch, compare, repair, and repeat. This is really the key reason to use a declarative model. This is the operator model in one slide. First, we declare the main resource is an InnoDB custom resource. That object describes the intended database shape, instance count, router count, credentials, storage, backup profile, backup schedule, and configuration. Then we observe, once the resource exists, we can look at resulting Kubernetes objects, pods, PVCs, services, secrets, and router. The running system is not hidden, but is exposed through the same Kubernetes API that platform teams already use. Reconcile. Reconciliation means the operator compares the dedicated cluster with the actual cluster and creates, patches, or repairs resources until the two are aligned. This is the difference between a script that runs once versus a controller that keeps watching. Fourth is the repair. If a pod disappears for any reason, Kubernetes replaces the pod. The InnoDB cluster and the MySQL operator work together so the database runtime converges after the failure events happen and ensure that the database topology is healthy again. As a result, the MySQL pods, sidecars, router, services, secrets, PVCs, and backup profiles stay aligned with the declared state. This is a high-level reference architecture for the demo. Inside the local Kubernetes cluster, we have the Orders API application. It's a small Flask app that writes orders and reads the database topology. The application is intentionally very simple because its job is simply to generate visible read and write activity while we operate on the database. The application then talks to the MySQL router. The router gives the app a stable endpoint. This is important because the app should not need to know which MySQL pod is primary or which replica is healthy. The router basically handles the database topology beneath the application layer. Behind the router is the InnoDB cluster, demo MySQL 0, 1, and 2. These are the stateful MySQL instances. They use persistent volumes for storage, and they participate in the replicated MySQL topology. The MySQL operator watches the custom resources and reconciles the runtime. kubectl talks to the Kubernetes API. The operator watches the InnoDB cluster and the MySQL backup resources and turns that desired state into actual pods, as well as services, PVCs, and supporting configuration. There are two dependencies outside the cluster for the purpose of this demo. Docker basically builds this image, and then the Kubernetes loads it into the local cluster. The MySQL backup PVC is the backup and restore target. When we run backup, the dump essentially gets stored in the backup PVC, and when we restore, the restore cluster initializes that from the PVC store location. There are four separate paths: the application data path through the router, the operator control path through the Kubernetes resource, the image path through Docker for image loading, and the backup path through the backup PVC. So with that, let's move on to the live demo. I'm using make here as a thin runbook layer. The important thing is not make itself. It's the day-to database operations that are expressed as repeatable automation against the Kubernetes API. So let's get started. So before we talk about MySQL, we need to make sure that we have the local platform working. So now let's go ahead and declare the database. Make MySQL applies the namespace, root secret, backup PVC, and InnoDB cluster. Make wait MySQL waits for a database and the router to become usable. So we basically have one custom resource fan out into real runtime, three MySQL pods, sidecars, router, services, storage, and backup configuration. We are not manually creating a stateful set. We are basically declaring an InnoDB cluster and letting the operator build the shape. So as you can see, all the three pods are up and running, each with two containers, the actual MySQL as well as the sidecar running inside of the pod. So let's move on. So we want to prove that these are real MySQL server containers, not just Kubernetes objects. So I can check the version of the SQL by running this command. And as you can see, we are running MySQL version 9.7.0 for Linux, x86_64, and we are running the MySQL community server. So everything looks good. Now, let's build the app image and load it into the Kubernetes cluster. We're going to do that by running make app image. I'm just going to go ahead and inbuild that. And the image tag is recorded as well. So the deployment uses the exact image that we built. Now, let's go ahead and actually deploy this app. This deploys the orders API, which, as we discussed, is a small Flask application that continuously writes synthetic order activity and reads topology, etc. Its job is to make the database behavior visible while we perform the database operation. The app is deliberately simple, but the database operations are really the star of the demo. So this one's good to go. Now we need to make the app available locally. So make port forward. So that's the command that's essentially going to expose the app locally. The dashboard and the raw endpoints will let us see the health, order activity, and topology from the app's point of view. The app itself does not know about the individual pods, but it connects through Kubernetes service plus the MySQL router. So let's go ahead and take a look at the simple app. So as you can see, this is the simple live order fulfillment app that we have created. It basically generates synthetic orders every couple of seconds. And as you can see, those get updated over here. It does display some information about the MySQL cluster that we are working with. It's essentially talking to demo MySQL 0, which is the primary write, as well as MySQL 1 is the read one. And we're using the demo MySQL as a stable Kubernetes endpoint. So everything looks good on that front. Now, just validate our cluster again. So as we discussed, there are three pods running. We have demo MySQL 0 as the primary one, and demo MySQL 1 and 2 are read only. Now, let's go ahead and start working on something interesting. So we are now actually going to demo a failover, and we're going to do that by running make failover. So make failover essentially finds the current primary pod and deletes it. Now Kubernetes replaces the pod, but the database recovery itself. So you'll actually see a brief interruption over here, and then it comes back up right away. So Kubernetes will replace the pod, but database recovery is more than that. It's more than the container restart. So the InnoDB cluster and the operator need to converge the topology. So as we wait over here, the demo MySQL 0 pod has been deleted, and it will get regenerated. But on the back end, as you can see over here, the InnoDB cluster and the operator have already changed, have already promoted the demo MySQL 2 as the primary write route, and the cluster is slowly getting back to normal with minimal interruption to this app that's running in the background. So let's wait for all the pods to come up, and let's check the state of the cluster after that. So as you can see, the demo pod uh, MySQL 0 has been deleted, and it's waiting for the replacement pod to be ready. But the app, as you can see, is already back up and running, and orders are being processed with minimal interruption. Great. So as you can see, all the pods are up and running, demo MySQL 0, 1, and 2. But the key thing that has changed is now demo MySQL 0 is now read only, and the MySQL 2 pod has been promoted as a primary. So that's a great example to show the backup and failover and recovery using the Kubernetes operator. So that all looks good. Next, we are going to demonstrate the config changes. For example, one of the things that we can change is increasing the number of or scaling the number of MySQL routers. So a clean example of a day two change is instead of manually installing another router, we can simply patch the InnoDB router spec and let the operator reconcile the number of router pods. So as you can see over here, the second pod is already being spun up. Let's kind of run it one more time. And as you can see now, both the pods are up and running. So this is a great example of day two change where we are basically adding a new router just by working with the Kubernetes operator. Just to go back up, we can do the same thing. We can scale down the number of routers as well. And as you can see, one of the router pods is being terminated. Let's check that one more time, and now it's gone. So now we are back to one pod. So that looks good as well. Another thing that we can change is changing the MySQL config. Then we'll basically run make config to run the patch to patch the config, and we can add these three parameters to the to the Kubernetes cluster: max connections, slow query, and long query. And as you can see, these are now reflected in the Kubernetes config as well. So again, all of these data operations are being performed by the Kubernetes operator. Now, another interesting we want to do is running a backup. So backup is basically a Kubernetes object. In this version, the backup lands on the local MySQL backup PVC, and the backup is observable. We can watch the resource move to complete it and see the output path as well. So as you can see, the backup has been created over here. Now the next step is to restore that. So it's creating clean restore cluster. So the key thing to keep in mind is that the script creates a new restore cluster, waits for it to become ready, and then runs Kubernetes job using MySQL shell load dump from the PVC dump. So it's going to wait for a few moments before the restored cluster is good to go. So the cluster is ready. Now it's waiting on the restore loaded dump. And it's good to go as well. So again, the backup and the restore looks great. The last thing I want to demonstrate was observability. So operators do not remove diagnostics, but they make the workflow observable through Kubernetes, such as operator logs, sidecar logs, etc. So just to reiterate, this is how we can check the status and get metrics and observability data from the cluster itself by running kubectl commands. So as we discussed, the operators do not remove diagnostics. They make the workflow observable through Kubernetes, such as logs, sidecar logs, so on and so forth. So these are the key things I wanted to demonstrate. Let's go back to our slides. So just to summarize, the database is still MySQL. We are not replacing MySQL with Kubernetes, but we are changing how the lifecycle is operated. Provisioning moves from manual shape and scripts to declaring an InnoDB cluster. That resource becomes the durable description of what the database should look like. Routing moves from hand-managed endpoints to router reconciled by spec. The application has a stable path into the database, even while the database topology changes beneath it. Recovery moves from a human-driven repair path to pod replacement plus topology convergence. Kubernetes replaces failed pods, and the MySQL operator and the InnoDB cluster work to bring the database topology back online and to a healthy state. The protection moves from a separate backup workflow to a PVC backup profile in the cluster spec. Backup and restore become visible Kubernetes resources that can be watched, repeated, and audited. So in summary, Kubernetes becomes the operational API for MySQL lifecycle, resilience, backup, and restore. I hope you found this demo and presentation useful. Again, the goal was not to demo every single MySQL feature. The goal was to show that the database operations can be expressed in a platform native way on a local Kubernetes cluster. The operator does not make database operations disappear, but it turns them into declared, repeatable, observable workflow. That is the practical value for teams that already use Kubernetes as their application platform and want database operations to fit the same operating model. Thank you so much for attending this session. I'll be happy to take any questions you may have. Thank you.